And generally, I encourage you to frequent the PIs before you present. Just wait for gravity a little bit.
Will the questions of the papers be on the internet?
No, I don't want to. So is there anybody that's not assigned to a paper and still needs to?
I am. I'm not sure.
You're not? So what are you waiting for?
I will do it later.
Yeah, please do it as soon as possible. I don't think there are much papers left.
Yeah.
Ah, on est obligé.
Winding down.
C'est énorme, ouais. Alors que j'ai passé son temps à me dire, oui, des dimanches, venez pour la présentation de The jungle. Jungle in the brain.
2 minutes.
C'est un peu ce chevelure aussi, non?
C'était déjà jeune.
Ouais,
Bah ouais, mais moi j'aimerais bien venir avec une perruque comme ça. Et s'il me demande qu'est-ce que c'est que ça, je dis jungle of the jungle in my head, like jungle in the brain.
Et au lieu de ça, t'as dit tout l'inverse finalement.
Ah, voilà.
Let's start.
You can start?
So the idea is that about 45 minutes,
45 minutes.
and then discussions and so forth will be.
In the 45 minutes also.
Okay.
We have 2 presentations.
Okay. So Arthur and myself are pleased to present you the article Rich Cell Type Specific Network Topology in Neurocortical Microcircuitry, which has been written among others by Idan Segal. So, the general goal of this article is to uncover structural regularities and architectural topologies of cortical microcircuitry. Why is it interesting? Because these topologies can have a deep impact on neural computation, functions, and dysfunction. Indeed, synaptic connections have proved to constrain the dynamics of the network, of the field. What has been done until now in terms of the past research? First, we have a growing body of microconnectomic data at our disposal. Second, this data has been used to map large-scale circuits at the synaptic level. And why? In order to characterize connectivity patterns between different pairs of cell types. In addition, there have been efforts that have been put to reconstruct neocortical microconnectomes using electron microscopy. And finally, some computer-generated predictive wiring diagrams of neocortical microcircuitry have been realized. And the general approach of this article is to analyze large-scale cellular level connectomes. So now we'll discuss the general methodology of this article, that is the reconstruction method of the in silico column and the statistical analysis.
So the reconstruction of the NMC is from somatosensory neocortex
You
of
don't know
young.
what's NMC.
It has been defined before. It's neocortical
I don't think
microcircuit.
anybody remembers.
Okay,
I
neocortical
almost don't remember
microcircuit.
myself.
From somatosensory neocortex of young rats, P14, and it has been done algorithmically and with adding biological constraints. And one of the first steps was to fix the number of neurons, about 30,000, in a small volume of 0.3 micromillimeters cube, grouping 55 morphological types with 13 excitatory cell types and 42 inhibitory neurons, making 36,000 synapses based on a distance-dependent probability of connection with an overall sparsity, that is to say, probability of single connection of 0.8%. And then further additional constraints were added on the number and strength of synapses. And
just slowly, just because it's a lot of data. That's something that I learned. I didn't know myself. If you look at the cortex, at the column or the circuit in the cortex, the probability of connection between two cells is 0.08%, isn't it? A very small percent on average, the connectivity. Although it's a very packed circuit, the probability for two cells to be connected is below 1%. Really quite
In your column or in general?
in general. So this is one example, this little thing, that cubic millimeter or so. But in general, if you look at two cells in two nearby cells within this range, very, very small percentage. Still, it makes within this volume almost 40 million synapses. So many synapses, but of course there are much more possibilities for connection. It's a very low probability. On average, of course, if you look at specific cell type, let's say between pyramidal layer 5, it could be 5%, but on average, very, very low. And that's important to remember.
And those
slowly, because
okay.
there are a lot of numbers and things to remember.
And those 55 morphological cell types were positioned according to their location across the six layers of the cortex, with layers 2 and 3 fused together. And those graphs check that the in silico normalized density of neurons and Booton density, synapses per connection, and PFP amplitude match what is found in vitro measurements. So here you see that it's quite nicely match the identity line between what is observed within the NMC, neocortical microcircuit, the reconstruction, and what is observed in vivo.
Is this private? Was they constructed that way?
Sorry?
Were the models constructed that way? Is this a result or a control?
Well, for the Booton density and for those three graphs, it was expected to be like that, because it's part of the additional constraints that were on purpose added. But I think this one was like an emergent result. There hasn't been the normalized density of neurons.
So could you explain what it is? What is the normalized density of neurons?
I don't know with respect to what it's. I can't remember with respect to what it's normalized, but it's the density is number of neurons per volume unit, so it has been normalized with respect to.
It was cubic millimeter. But I think it's a very good point that we have to discuss, because there is, when you build such a circuit, and you take many, many cell types and 6 layers, and you put the number of cells correctly, so to speak, as much as you know in volume, there are 2 levels of validation. First, you want to make sure that what you put, because there are so many parameters and so forth, fits what is known while you build. So this is not, as it was commented, it's not a surprise that there is a matching between what you put and what you get. But it's not always the case. You have to make sure that it really happens. That's one aspect about validation. Later you will see that there are things that were not assumed and emerged from the circuit.
Yeah.
But that's the validation process of that what you did is really what happens in the circuit. Also, I should mention, and this is technical thing, but for example, pair recording from cells, from two types of cells, there are 55 types of neurons in the circuit. In this case, it's a morphological type. So layer 5 pyramidal cell is a type. Layer 4 spiny-stellate cell is another type. There are 55 types of morphologies in this circuit. And in terms of recordings, biologically, maybe there are 10 pairs types that were recorded. So say layer 5 to layer 5, layer 4 to layer 4. Out of these 55 multiplied by 55 pairs, only very few were recorded experimentally. So in this circuit, what was known was taken into the circuit, but a lot of things are not known. Yet, nobody knows. So we don't know what is the probability for layer 2, 3 to be connected to layer 6. We just don't know. So there is a lot of open, so to speak, unknowns here. Some were validated later, and some are still, and probably will ever remain unknown. Because nobody was going to record from 55 multiplied 55 pairs, in vivo, in vitro, and things like that. When we shall have the connectomics reconstructed, which we don't have yet, maybe next 5 years, as I mentioned in last talk, then we can maybe validate other aspects that are there and we don't know if they are correct or not. So we have to make clear that what this circuit is a draft. It's a draft circuit. The best that is available today in terms of putting the data together, but we don't really know that statistically everything that happens in this circuit happens in this circuit. We don't know.
So now we can discuss briefly the methodology for the statistical analysis. So we define 3 connectivity matrices. The matrix A, where coefficient ij is a binary number whose value depends on whether or not there is a connection from neuron I to neuron J. The matrix B, where coefficient ij is a number of synaptic contacts per given connection from neuron I to neuron J. And the matrix C, where coefficient ij is the total conductance from neuron I to neuron J via all the synaptic contacts. So A and B are structural matrix, while C is called the functional matrix. And so it's interesting to note that B and C quantify the strength of the synaptic connection. And then the general methodology of the article is to test whether the NMC network displays connectivity more than expected by random. So for this, we define 2 reference random networks. The first one, Erdos-Renyi, or uniform connection probabilities. And what does it mean? It means that the probability of a connection from any neuron I to any neuron J is the same, P. And then we define also the distance-dependent random network, where the probability of a connection from neuron I to neuron J is non-uniform and depends on the intersomatic distance between the 2 neurons. So these are the
one little thing.
Yes.
Just want to comment on B. So I don't know if you're aware of it, but in the cortex, whenever a cell makes a connection to another cell, which as I said, very low probability, but when there is a connection, it's always more than one synapse, which is absolutely not trivial to understand, because if you just throw axons and dendrites, there will be a much more higher probability for one connection and smaller probability for 2 connections between one cell to another. But in reality, it's very different statistics. And for example, between layer 5 pyramidal cell to layer 5 pyramidal cell, there are 5 connections on average whenever they are making contact. Very rarely, but when they do, it's 5. Between inhibitory neuron to an excitatory neuron, it's typically 12 connections per contact. So it seems somehow that in development or through plasticity, we don't know why, how, when 2 cells are connected, they make sure that they are strongly connected, not by
these are the four main results presented in the article. So emergence of excitation-inhibition balance. We will see that the strength of synaptic connection, which is the number of contacts and the conductance, is likely to compensate the large imbalance in the raw number of connections. Cell type specific in-hub and out-hub neurons forming the rich club. We will see that neurons with a lot of incoming connection and a lot of outgoing connection, these are the hub neurons, are densely connected to each other and hence organized into a rich club. Cell type specific triad motifs. Here we will discuss that some particular motifs of 3 neurons are overrepresented in our cortical column, and this overrepresentation is cell type specific and varies across the different layers of the microcircuit. Structural and functional small world topology, we see that these hub neurons we mentioned before are densely connected with a short average distance between any 2 neurons, and hence they tend to form local clusters, and these local clusters can have an impact on the functional and computational role. So the first question is to quantify the structural ratio between excitation and inhibition within and between the two populations of neurons, that is excitatory and inhibitory. So we consider the raw number of connections, that is our binary based matrix A from before. So if you look at graph A, you can see the distribution of the connection. In red, you can see the excitatory population. In blue, the inhibitory population. And one first comment is that the distribution of this connection is highly asymmetrical. You have much more excitatory connection than inhibitory connection, and this might suggest a structural imbalance in the network. Then we consider incoming connection at the level of a single cell. So each cell has a certain number of excitatory incoming connection and a certain number of inhibitory incoming connection. So if you look at graph B here, you can see the relationship between these two numbers for each cell. Each dot represents one cell. It has been plotted separately for excitatory population in red, in various shades of red for various morphological types of excitatory neuron, and the same for the inhibitory population. Here you can see a linear correlation of 0.62, and this suggests that the ratio of these two numbers is constant from one cell to the other. And this phenomenon,
What are the dots? What is it?
each dot is one neuron, and you can see the linear relationship between the number of excitatory income. It's fine. So then you can look at graph C. You have the distribution of these ratios. If you consider the ratio of the number of excitatory incoming connections versus over the number of inhibitory incoming connections. Again, the blue curve is for the inhibitory population and the red curve is for the excitatory population. You observe an average ratio of 6.6 for the inhibitory and of 13.8 for the excitatory population. So one notable fact is for the excitatory population is that the ratios are on average about an order of magnitude. So the conclusion from this slide is that the ratios of the number of excitatory incoming connections over the number of inhibitory incoming connections from one cell to the other is fairly constant. And this is true for the excitatory population and less obvious for the inhibitory population. And the second fact is that this suggests a structural imbalance in the excitatory versus inhibitory incoming number of connections. And then the author repeated the same process than before, but now they consider some notion of synaptic strength instead of the raw number of connections. So that is with the matrix B and C from before, that is respectively our number of synaptic contacts and the total conductance. So again, each cell has a certain number of excitatory incoming synaptic contacts and a certain number of inhibitory incoming synaptic contacts. And they consider the distribution of these two numbers for every cell. And if you look at graph F, you can see again the distribution of this ratio. Again, the red curve for the excitatory population and the blue curve for the inhibitory population. You observe an average ratio of 3.5 for the excitatory population and about 3.7 for the inhibitory population. And the interesting fact is that this ratio has been reduced quite significantly relatively to those observed when considering the raw number of connections. And on graph I, here, you observe the same thing, but for the conductance. And again, the ratios of incoming conductance, of excitatory incoming conductance versus inhibitory incoming conductance has been again reduced. So the two conclusions from this result is first that the two notions of synaptic strength, that is our number of synaptic contacts, our matrix B, and the conductance, our matrix T, display more balance, and this might somehow compensate the structural imbalance observed when considering the raw number of connections.
Are you going to ask questions or only I will ask questions? Would be good if you will ask questions. For example, why did it disappear in the beginning in terms of number of contacts, not connections, but contacts? There is a big imbalance. Per cell, you get about 10 times more excitatory synapses than inhibitory synapses. If you just count how many inhibitory cells talk to me and how many inhibitory excitatory cells talk to me, I get 10 more excitation than inhibition. Okay? That's highly unbalanced. But if you take into account number of contacts, because what I said before, and this should have been puzzled you unless you understood it very fast, the fact that you get per contact more inhibitory contacts than excitatory contacts, let's say 5 contacts from one excitatory to one excitatory, and let's say 12 contacts from inhibitory to excitatory, this decrease the imbalance, because if you count the number of contacts, you get on the average 1 to 4 rather than 1 to 10. Okay? Then there is the issue of conductance. Apparently the inhibitory conductance is stronger, is larger than the excitatory conductance. So this again improves the balance even more, because you understand that the brain cannot function if it's not in a somewhat balanced state between excitation and inhibition. There is too much excitation, the whole brain will start to become epileptic. So the whole notion of balance is that you need somehow that the inhibition and excitation will be coordinated, and there is a beautiful theory of Chaim Sokolinski in science about what does it mean that the network is unbalanced and doesn't go either dead without activity or too much activity. So you need this balance. So the question is here, how do you get the balance? If you get the balance, what makes the balance? So this was the direction of the question. But really ask questions, because this is not clear what is happening here.
So the second part of the presentation deals with cell type specific in-hub and out-hub neurons forming rich clubs. So let's first define the degree of a neuron. It's the number of presynaptic cells, so this is in degree, and postsynaptic cells, out degree, of a given neuron that reflect either that tries to quantify the input to neurons, so the degree of convergence to the neuron, or this is for in degree, or to quantify the divergence with out degree. And if we look at the distribution of in and out degrees for all the neurons in terms of number of connections, so relative to matrix A, we find in both cases a monomodal distribution that slowly decays, so is skewed on the right for both in degree and out degree, with a mean that is approximately similar, about 250 connections, but a very long tail here that decays slower than an exponential, but if you fit it, but faster than a power scale. And it has been suggested that because the power law decay is scale-free, it might reflect some kind of metabolic cost or biological constraint on the NMC.
One second. 10,000 synapses, let's say. And here you see that some of them get, let's say, 1,000 synapses, so 90% of the synapses are coming from outside this circuit. That's important to remember, that when I'm a cell, and most of my connection is coming from outside my cubic millimeter, not from inside my cubic millimeter.
Is this for excitatory and inhibitory DNA?
Yes. And so how to explain this degree heterogeneity between in terms of morphological properties? Can we explain this? Because intuitively we might think that the integrity depends on the total length of the dendritic arbor and the outer degree of the length of the axon. So a scientist precisely plotted the total dendritic length for all the neurons. So each neuron is a dot here as a function of in degree, and the total axonal length as a function of out degree, and they found quite nice linear correlations here, better for in degree than out degree. And this is when you collapse all cell types together. But when you consider specific cell types, you have even greater. For example, here it's a pyramidal cell from the layer 5. You find really good correlations close to 1, and overall for most of subcell morphological subtypes you found correlations above 0.8, very good correlations. So indeed morphological properties can probably explain this in degree and out
So
degree.
this is not surprising. You would expect that if I have a longer dendrite, I will probably get more synapses. So there is some density of synapses along dendrites, and if I have double the length of dendrites, I will probably get double the number of synapses. And also if I have longer axon, probably I will make more contacts. Not always the case, because as you know, the axon has these butons, the presynaptic side. Some axon have dense butons. Every 4 micrometer you will have, some of them have every 10. Not necessarily directly connected to the length of the axon, but it is related to the length of the axon. So that was what we found, which is expected, but we have to show.
So a hub neuron is a neuron with high in or out degree. It is sketched here on the graph on the right. So here we defined, we are interested in the neurons that have either high in degree or high out degree, around 1,000 synapses in the last half percentile of the distribution. And we found that, so it's about 157 neurons. And we find that we have a very small class of neurons that make use either in hubs or out hubs neurons. Only pyramidals here for when you consider the number of connections, so the structural connectivity. But if you look, if you now consider the functional connectivity, if you try to weight it in terms of conductance, then in-hub neurons are still excitatory, pyramidal cells, but out-hub neurons become mostly inhibitory. And their distribution is such that most of in-hubs are positioned in deeper layers of the cortex, and most of out-hubs neuron are in intermediate layers of the cortex.
To understand that a hub in the computer world, a hub is something very important, because there is a lot of connections coming to this computer hub, or maybe this hub makes a lot of connection to other computers. So this hub is very important. For example, if you have an attack on the hubs, if you attack a hub, then you can destroy the whole network. So it's very important to understand which are the hub cells in the cortex, because if there is a disease that is specific to the hub, if there is such a disease, then you destroy the whole, you break down the connectivity in the network. So hubs are very important functionally and structurally. And so nobody ever tried to look who are the hubs in the cortex, who are the important cells that you have to be careful not to destroy.
and it can be noted that there's no real particularly here, there's no intersection between the neurons that are in hubs and out hubs. There are different neurons that are in hubs and out hubs. And because I said they were in different, also in either deeper layers or intermediate layers. These are not the same. And finally, rich club is a topologically integrated network feature that comprises greater than random connectivity between a relatively small number of high-degree hubs. So it's maybe easier to understand it graphically. Here, the orange nodes are either receive or send many projections, so those can be considered as hubs, and they tend to be more connected together than it would be expected in a random network with neurons that would have a similar number of connections. So here in the NNC, do have neurons form rich clubs. To quantify it, we can define a rich club ratio. If you take the total degree of neuron, the total degree is the sum of in degree and out degree, and you count the number of connections that a neuron of a certain total degree D make with other neurons of degree greater than, equal or greater than D, and you divide by the number of connections you would find by simulating such a random network with the same probability of connection. You can define a rich club ratio which is non-significantly different from 1 up to a total degree of about 300, and then for neurons that, and then the more neurons have a total degree, in degree or out degree, then the more then they tend to form rich club and have a high rich club ratio, which is significantly higher than 1 here, about 1.5. So at least in the NMC we have a rich club organization, and maybe also in the cortex. I think we have some experimental evidence of, notably in T. elegans and in Drosophila, of rich club organizations.
I understand the term rich club, but I'm already rich. Like rich people like to meet each other, yeah, and have clubs. That's the origin of these terms, you know, and that's what happens in the cortex apparently. If I'm already rich with synapses, I like to make connections with somebody who is like me. We can share the money together and rich them. It has a functional meaning, of course, but I mean also in politics, you know, rich people influence the politicians. Politicians make connections for in-hub and out-hub, and that's another thing. But that's interesting. And we don't understand yet what made it happen. We don't completely understand yet, because we built it. We should understand everything because we built it. We don't yet understand the emergence of rich club. What is the origin? Why, when I get a lot of synapses, I also tend to make synapses with others that make a lot of connections. But we are studying this now.
Do you think that's true across the columns as well? That we're looking at now just one column, but you think hubs from one column also connect?
Probably no. Actually, we didn't discuss it, but this column, which contains 30,000 cells, is now, so it's a big matrix. It's 30,000 by 30,000, and we know which one is connected to here. But now we have a circuit that also contains 6 other circuits, similar circuits around it. So there will be no boundary conditions at the end of this circuit. So it's extended now, and yes. So if you take a little bit of a surrounding circuit, which makes it more than cubic millimeters, so it's you saw that there is nothing happens until a certain point. There must be something more, because otherwise you would expect something that grows as you have more synapses. You tend to make more than expected. So it's very important that whenever we say something, you always have to compare it to a random network that with similar statistics but random. This line of comparison is the case of per case of number of, let's say, number of in-house, number of you build a random circuit that has the same distribution, and you ask whether there is a rich club or not. We found that you have to go up to really extremes, and only then you start to see this rich club formation. So it's beyond the number of synapses. It's something that happens in a given number of synapses, and this is the point we don't complete. What is this point of change that we're studying? But the intuition is correct.
Okay. So now we consider a particular topology of interest between a pair of neurons, which is called the reciprocity. A connection can have three possible. A connection between two neurons can have three possible configurations. Either neuron A sends a connection to neuron B, either neuron B sends a connection to neuron A, or there is a reciprocal connection between both. So in the ER reference random network, neuron A sends a connection to neuron B with probability P. So the probability of a reciprocal connection between both is P squared because both events are independent. So the question we are not trying to answer is how well our ER and distance-dependent reference random network can capture the reciprocity from the NMC column, that is the propension of the reconstructed in silico cortical column to form reciprocal connection. So if you look at the graph on the slide here, you can see reciprocity plotted versus sparsity. So the reciprocity is the probability of a reciprocal connection. The sparsity is the probability of a simple non-reciprocal connection. Why is it called sparsity? Because it takes a low range of values. So you can see here the curve y equals p squared, which shows the reciprocity in our ER random network. And if we consider the reciprocity here for various cell types, so for the excitatory population here, for the inhibitory population, for the global NMC column, and for various morphological layer of the excitatory population in the various shades of red triangle, and for the various morphological layers of the inhibitory population, you can see that the reciprocity is always shifted up as compared to the y equals p squared curve. So what do we learn from this is that clearly our ER random network does not capture the reciprocity inherent in the NMC column. So we can continue to test how much ER random network and distance-dependent random network capture the reciprocity in the NMC. So if we consider a measure to test it, which is called the hyper-reciprocity level, which is the ratio of the probability of a reciprocal connection in the NMC over the probability of a reciprocal connection in our reference random network, that is p squared. And if you look at graph B here, we want to test whether ER captures the reciprocity in the NMC. So here you have plotted the distribution of the hyper-reciprocity by simulating 100 times the ER random network. So you observe that the hyper-reciprocity is about 3 for the global NMC cohort, about 2.3 for the, about 2.5 for the excitatory population, and much larger for the inhibitory population. So what does it mean indeed that ER does not capture the reciprocity in the NMC column? And you can observe the same phenomenon when you plot the distribution of the different cortical morphological layers separately. So now if you look at graph C here, we test the degree of reciprocity, so the hyperreciprocity, with, again, the distance-dependent random network. Again, you have the distribution of hyperreciprocity computed by simulating 100 times distance-dependent random networks. And the interesting fact is that these hyperreciprocity ratios, when computed against distance-dependent random network, have been reduced as compared to tested against the ER distance-dependent random network. You can see about 1.2, which was about 3 in the case of the ER random network.
Just, I think that we should really go on because we don't have much time. Just to say that you didn't show, but if you look at the circuit, there is a distance-dependent probability for connection. If you just look at the circuit and ask what is the probability for nearby to make a connection cells, it's higher than if you go away in the circuit. So there is a distance dependency of probability for connection. And if you take this into account and you build a random network that takes into account the distance dependence, then you can explain most of this reciprocity. Okay? So of course the question is, what is your reference random? There are many types of random networks to compare with. The most fundamental one is Erdős gradient, which is completely random, there is no distance dependent nothing. And if you take the distance dependence and build the random network with distance dependence, then you can explain the reciprocity. So the whole idea is to try to explain all the statistics you achieve by building random networks that some principles that enables to explain everything. Then you say that you understand the graph. But maybe you should go on. You have, I think you have one more thing to show, or
we have
you want to say, you have many, but you want to say something that is maybe about triplets, or?
Yes,
okay.
the next.
Okay. So, just the conclusion from this slide is that distance-dependent random network capture reciprocity much more than ER. And what does it mean? It means that the probability of a reciprocal connection in the NMC is highly dependent on the distance between the two soma of the two neurons. So now we consider another particular topology of interest, which is a topology between 3 neurons, the triad motif. You can see here that the triad can have any of 13 possible configurations on the graph A here. So the question we are trying to answer here is again, are there some triad motifs which are more overrepresented compared to our reference random network? So for this we define the Z-score, which is a measure of representation of a certain triad motif in the NMC relative to the reference, the given reference random network. So we want to test how much a certain triad motif appears more than expected by random. So as you can see here, what is the Z-score is for each triad I, you compute the number of time the particular triad I appear in the NMC column, minus the average number of times the particular triad motifs appear in the tested random network over the standard deviation of the number of times the particular triad motifs appear in the random network. And we compute this Z-score for each of the 13 possible configurations. We compute this Z-score also for 3 different random networks, ER with reciprocity, and our distance-dependent random network. And so you can see that clearly some particular triad motifs are overrepresented as compared to any of the random reference networks. So you can see the 4, the 9, the 10, the 11, and 12. And if you look at graph B, you observe the same phenomenon when you do the same process separately for the excitatory population and for the inhibitory population. So then we we did the same process than above, but for different morphological types of neurons. So if you look at graph C here, you see the overrepresentation of some triad motifs in the NNC for the 13 possible morphological types of excitatory neurons in various shades of red. And you can see that some prototypical triad motifs emerge, like the 3, the 4, the 10, and the 11. And the author defined these prototypical triad motifs as transitive. What does it mean, transitive? It means that when you have a connection from a neuron I to neuron J and from a connection from a neuron J to neuron K, this implies a connection from neuron I to neuron K. And this property appears in all of these emerging triad motifs. And now we can focus on graph D. You see also again the representation of some triad motifs in the NNC for 11 morphological types of inhibitory neurons, and this time two triad motifs appear more than expected by runtime, which is the 3, which is called the divergent triad motif, and the 4, which is the feed-forward triad motif. The conclusion from these two slides, in short, is that we have an overrepresentation of certain triad motifs in our in silico reconstructed model, and this overrepresentation is cell type specific.
Well, because we have to finish, can you go back? This was the most unexpected result in some sense, because and the last time there was a meeting here with Gatsby and was Larry Abbott and other, Peter Dayan and other theoreticians. This was the most interesting thing, because why? Because this red thing that you see below is an experimental result. So in the experiments of people who recorded from triplets, and Henry Markram recorded from 12 cells simultaneously, because you need to know the statistics of connectivity in the cortex, and the only way to do it really directly is by in vitro patch recording from many cells. These red things that are highlighted below, all the green things, are experimental results. This was not, as before Matti asked, this was not put in the circuit. We did not know in advance that there will be these triangles overexpressed or underexpressed. This we did not know. So now this is a nice validation, because the experiments, which are the red triangles, agree with the theoretical prediction, which is the graph. So this means that you are born, probably. We are born with triangles like this. Because this is just geometrically putting things together. There is no plasticity in the circuit. We didn't do any plasticity. We just put things together and connected them. And we get this structure. So this structure is probably inborn. You are born with these triangles. And you find them in experiments, both in CAD, in visual cortex, in somatosensory cortex. Whenever you record from more than 2 cells, 3 cells, 4 cells, you get this overexpression. So that's very interesting. That there is a skeleton that is built in when you are born, probably, maybe, but at least experiments show that. Of course, in the experiment it could emerge from plasticity, but in our case there is no plasticity, just geometry. And the question is, what does it mean functionally? That's an open question in terms of memory, in terms of dynamics of the circuit. What does this overexpressed, underexpressed structure mean functionally? We're open. We don't know. And that's, of course, the next thing to explore. So maybe you just summarize what you think, or maybe open questions that you think are important. We cannot go over everything.
Okay, so let's.
It's a long paper. It's a long paper in Nature.
Okay, so we skip small worldness, maybe. We'll go to the conclusion.
Maybe just say a word about small worldness.
Yes, okay.
Very fast, because just a word.
Small worldness is the tendency for neurons or networks to build long-range interaction with the shortest path length possible, and the tendency to cluster together. In terms of information, it reflects the balance between global integration of information with building long-range connection, and local segregation of neural information, building small clusters, small networks. And it can be summarized by the small world index here. And so if you compare, you normalize but what you would expect in a distance-dependent network, and we see that in the NMC, the baseline is 1, so there is no particular small world organization compared to a distance-dependent random network. While in the NMC we find a global small world index of about 2, and here is for the excitatory and inhibitory populations. So inhibitory has an even greater small world index, and here for all the cortical layers and excitatory and inhibitory population. And this is only based on structural connectivity. If you want to take into account the strength, that is the conductance and the sign of the synapses, either positive, excitatory, or negative inhibitory, you can redefine another metric, the weighted small world index, which is proportional to the product of the weights, the synaptic weights on a given wave from neuron I to neuron J for each synaptic relays, and which is, well, here is the formula. It depends on the sign, but well, it is, yeah.
I just want to say a word about small world. We know that we are a small world. Humans are small world. So if you take two people in the world and you ask what is the distance in friendship between two people is about 6. Then you know that if I take a Brazilian and a Chinese and so on, and you ask how many people connect them through friendship, Facebook friendship or something, it's about 6. I mean, the cortex is about 2.5. So between the friendship between two cells, in terms of number of synapses on average, it's the curve is 2.5. Very, very close friendship, which means a lot of information transfer very fast between, on average, between. So let's complete.
So now we try to resume everything shortly. In this table, we will resume the main topological findings and try to relate them to their possible functional role. So at the beginning, we discussed the constant excitation inhibition ratios for excitatory populations. We also discussed the synaptic strength balance, which might compensate the connection-based imbalance, and this property might suggest a balanced state of the network. We discussed also hub neurons with a lot of incoming connection and a lot of outgoing connection, and these hub neurons are only found in a very small number of cell types, and this property might have an impact on the collective behavior of the whole network. These hub neurons are densely connected between each other into a so-called rich club, and this property might facilitate efficient communication across the network with short synaptic delay and low noise. We also mentioned that certain triad motifs are overrepresented in our reconstructed column, and this overrepresentation, we saw that it was cell type specific and might allow the sustaining of the activity of the network. So this means we are talking about memory, a memory property. And finally, the small world topology, which is enhanced when the synaptic properties are considered, and this property is likely to improve both responsiveness and synchronization of the neuronal network.
And we raised some, well, can we talk about some limitations of the model? Well, of course there might be inaccuracy in the reconstruction due to uncertainties on the measurements for axonal length and synaptic conductance. The connectivity has not been completely well captured by in the simulations, and there were no plasticity rules at all implemented in it. But still, in vitro and in vivo empirical results corroborate some of the findings here. For example, the existence of redundant synapses. Triads and clustering coefficients were not fully captured by distance-dependent random networks, so there is a need for higher order generative models, one that do not consider isotropic probability of connections, but the fact that neurons are oriented in certain directions. The data come from P14 rats. We do not have a mature brain. However, evidence of network properties such as ball-worldness and the rich clubs, hub neurons, have been found in other mature cortices, for example, the cat cortex, visual cortex, I think, and also across different species at different developmental stages. And some of the questions we raised are about the balanced regime of the NMC. Is it balanced according to the mathematical definition of a balanced network? So that would mean that we can find that neurons fire asynchronously if we try to inject in them some activity, look at their activity, and also that, according to some of the predictions, that the conductance of individual neurons scale with the inverse of the square root of their mean degree. So that could be checked probably quite easily by further statistical analysis. And also we can consider more types of connections, not only excitatory or inhibitory, but excitatory, excitatory, to have a full picture of the connectivity, and probably also higher order motifs, not only triplets or triadics or diadic motifs of neurons, but maybe 4 or 5 greater clusters of neurons. This article focuses mainly on shortest path or strongest path between two neurons, but in fact, to give a faithful account of the complexity of the communication within the nervous system, once you consider the integration along all the paths, because this implies time delays, as we said during the last talk, and delays are important for neural computation. And also it can be noted that some of the metrics tools that were developed in this article, for example, the weighted small world index we briefly talked about, could be used in other fields, in studies of other types of networks, for example, social networks, Facebook and any
You
types of
mean something in Facebook that there will be not only friendship, but also antagonistic friends, or the minded friends, which needs another theory. There is no theory, there is no analysis yet with science. So now it's friendship, yes, but what about these people that hate each other? And that's what happens with inhibition, yes, so they hate each other. So we have to develop a new graph theoretical approach. Thank you very much. Questions or not very fast before we take a little break? Ask the people here.
First, why, like, we think that overall there should be a balance between expression and inhibition, but are we sure that we need a balance in small networks like the columns that we see here? Maybe the balance is in more general networks.
It exists at different scales in the brain. And it's a small network, but it's quite a big network already, 30,000 neurons.
And also, what we showed, the statistics, are not likely, is not a concrete proof that there is a true balance between the two in the networks. Because you see that the average ratio is about 10. It has been reduced to 2 when you consider conductance. So it's likely, it might suggest that there is some balance, as described in the paper from Sampolinsky about the balanced network, but it's not a clear proof in the statistics shown here.
First of all, you have to remember that when you go out of the circuit, there is less and less inhibition coming in. Because most of the long-range connections in the cortex are excitatory. So from the thalamus to cortex are excitatory synapses, top-down excitatory. And so long-range axons typically are excitatory. So if you take into account more, you will get more excitation relative to inhibition. So that's one general comment. So you can't get better balance by going away and get less, in principle. But I have to also mention, and that you really need to look at the new paper by Sampolinsky and his team in neurons. So you don't need to have the same number of connections in order to get a balanced system. You don't need to have the same number, because this is the recurrent circuit. And the question is, when is the circuit recurrently is balanced? And he shows a mathematical proof of what are the conditions. And the conditions are not at the same number of excitation and inhibition per cell, but some kind of global ratio. But this is the other paper. But it's very hard to grasp what does it mean as balanced network. It's not by numbers, it's by dynamics. It's by numbers.
ouais,
So
ouais,
this
ouais,
can
ouais.
easy to explain such statements.
This was good. Thank you.
Thank you very much.
Non, en fait, ils ont reconstruit le réseau par ordinateur. Et après, ils ont fait ça.
Il reste le réseau.
Après,
Sur l'information de base, c'est pas le
non, non,
compte.
regarde, ça, non, moi, c'est pas du service. En fait, ils savent que la biologie dit, par exemple, il y a telle statistique qui sont présentes dans la biologie. Ça veut dire, par exemple, le fait qu'à cet endroit du cortex, il y a telle densité de connexion entre les axones et les synapses. Il y a telle densité de connexion. Et donc, toi, ce que tu vas dire, c'est que tu vas simuler par ordinateur un réseau de neurones qui correspond, dont les propriétés statistiques correspondent aux propriétés
Une nouvelle
biologiques.
statistique qui émerge a
C'est
posteriori
ça,
de
c'est
ce
ça.
que tu connais a priori.
C'est ça.
C'est la demandé à
C'est
Mathis.
ça. Non,
Parce que au début, lorsque c'était des résultats qui émergeaient,
ouais.
alors au début, c'est les conditions de jeu que vous avez rentrées dans le
C'est ça.
pour pointer dans le résultat.
Ouais, c'est ça. Et donc après, tu vois des propriétés qui émergent sur les qualités, les slowness.
Vous êtes d'accord que si tu rajoutes une condition de base a priori, alors ça va être plutôt des... Enfin, ça change beaucoup de choses, par exemple. Mais maintenant que si tu vas implémenter ça dans le réseau, ce que tu as appris maintenant, alors tu peux découvrir encore d'autres.
Ah ouais, le réseau, il est inactivé. C'est capable d'activer en injectant du courant, soit en stimulant.
Genre un output fonctionnel.
Laisse parler.
Alors, יפה. So, hi, my name is Elisheva and this is Levi, and we are going to present the paper Increased Prevalence of Calcium Transients across the dendritic arbor during plate field formation.
I just want to mention, I forgot to do it last time. Whenever you present a paper, you really should say where it came from. You know, what is the reference? For example, this is a neuron paper. It's important to know because then people can see. So and also the paper itself or the journal itself means something in some sense to the importance maybe of a paper. So it's always important to say where did it came from. The previous one was Nature Neuroscience and this one is Neuron.
In his lesson, Professor Idanseyev talks about how we conceptualize a neuron. We know that the neuron consists of soma, dendrites, and axon, but usually in order to simplify our model, to remodel it as a point. The reasoning behind this simplification is that the action potential, which is the spiking of the neuron, occurs at the soma. So oftentimes when we speak about the behavior of the neuron, we speak about what is occurring at the soma, and we tend to ignore the complex computational role of the dendrite. This paper will not only illustrate the fascinating mechanism of how plate cells are formed, but will illustrate the important and fascinating role that dendrites play. This will illustrate the value of thinking about the neuron as a multi-unit structure. Maybe one of the reasons why the computational significance of the dendrite is underappreciated is due to technological limitations. Until recently, it was hard or even impossible to record a neuron in specific dendrite or in the dendrite and in the soma at the same time. So now I'm going to remind you some concepts that will be useful for understanding the paper. The first is a plate cell. A plate cell is a type of a pyramidal neuron within the hippocampus that becomes active when an animal enters a particular place in its environment. This place is known as plate field. So in the picture you can see the mouse that's going on the track, and every section of the track another cell is firing while the others are not. This is a slight simplification because really there is a tuning curve that is maximized around this plate field. What this indicates is that each cell seems to be encoding a particular location in the environment. And since plate cells are not only firing when the animal actually enters the particular location, but also during sleep and rest, this has led to the idea that plate cells represent a cognitive map of space, a type of mental representation which allows an individual to acquire, code, store, recall, and decode information about the related locations and attitudes of phenomena in their spatial environment. The next concept I want to remind everyone is synaptic.
So just, you heard before about plate cells and grid cells. It's not something new
No, it should not.
and you know that there was a Nobel Prize on this particular 2 years ago or so.
So the next concept I want to remind everyone is synaptic plasticity. Synaptic plasticity is the ability of synapses to strengthen or weaken over time in response to increases or decreases in their activity. I assume that everybody should be familiar with this concept. There are several underlying mechanisms that cooperate to achieve synaptic plasticity, one of which is the change of calcium release. This will be an important feature of synaptic plasticity, so keep it in mind. One of the main questions the researchers in this paper want to address is whether synaptic plasticity plays a role in the formation of plate cells. Indeed, if we disrupt synaptic plasticity through NMDA inactivation or CAG2 inhibition, which are the mechanism underlying synaptic plasticity, then we see behavioral defects in spatial navigation tasks. Okay? Is synaptic plasticity required for the formation of new plate cells? I just mention one reason why we would think that synaptic plasticity is important for place cell formation. But on the other hand, there are some results that might put this idea in question. For example, if you interfere with synaptic plasticity in the hippocampus, place cells do still form. In addition, place cells seem to form upon the animal's first traversal across the nova environment, which will seem to underlie the idea of the learning process. How can synaptic plasticity operate under a single exposure? So, did you understand that research question? Okay. So the general approach to uncovering the role of synaptic plasticity in place cell formation is to study the cells during their formation and to check whether synaptic plasticity mechanisms are connected to this process. In order to do so, we need to zoom in and study the activity of the dendrite. There are two measures of dendrite activity that Sheffield and Dombeck choose to focus on. The first is backpropagation action potential and the theoretically generated spike. They refer to this as branch spikes, also, which are thought to provide the postsynaptic depolarization necessary for heavy association when paired with presynaptic input. Okay? The second measure of dendrite activity that we'll be paying attention to is calcium transients, which I briefly mentioned before. On the dendrites, there are many calcium channels. Calcium flow in and out of the cell can depolarize the dendrite, making it more sensitive to presynaptic input. While previous research tried to infer branch spiking based on somatic firing, means action potentials occurring at the soma, this is quite problematic, since as Sheffield and Dombeck showed in 2015, branch spiking and somatic firing are dissociated. This means that any inference from one to the other will be highly tenuous. Fine? Okay. Now that we have the two-photon calcium imaging spectroscopy, researchers can directly record from the dendrite while simultaneously recording for the soma and tracking each dendrite back to its parent soma. Okay, so in order to test place field formation, we need to generate novel environments. The researcher used mice and a virtual reality system. The advantage of using virtual reality is that the mice will be exposed to novel environments without actually moving, which removes recording complications. So the procedure for mice were trained for 7 days on a 3-mile virtual environment. During training, the mice repeatedly traversed this track for 20 times. Subsequently, on experimental day 1, mice traverse a familiar environment 15 times before their environment is rapidly switched to one that they have never seen before. Mice then experience this environment for at least 20 laps. Okay? So the researchers saw that from behavioral point of view, the mice learn the new environment very quickly. Only in the first lap, the velocity was more slowly, but after it, there is no significant differences between the familiar environment and the novel environment.
Do they have any goal? Do they get something when they
What?
when they walk? They get something.
I
Yes,
think there's a reward.
water.
Yeah.
Water.
Is it location dependent?
No. They just run and
They have to learn to navigate the environment for
They need to
reward.
learn that.
Yeah.
The next question the researchers asked is whether switch from familiar to novel environment is causing a cognitive remapping in the hippocampus. Using two-photon imaging, they identified 347 brain cells that were active during the familiar environment and that tiled the wall track. After the switch from the familiar to the novel environment, we found that most of the place fields that were found in the familiar environment are not acting as place cells in the new environment. For those cells that were active in both environments, the place field in the new environment was not correlated with the place field in the old environment. An additional...
Maybe you want to point out, because it's very hard for people to follow.
I think
Unless you have a pointer for you.
Yeah.
No, let me tell you.
So the green, yes, you have the green cells here, and these are going to be place fields only for the old environment. And then if you look at yellow, the yellow cells, these are going to be place fields only for the new environment. And then you're going to have some overlap. So there's a few orange ones; those are going to be the overlap. But you see that most of them, there's very little overlap. Overall, it's basically a totally new set of cells. And there's no correlation for the ones that are in the orange, the ones that are place cells for both. There's no correlation in the locations. It's not going to be in the beginning of the track that this cell is going to fire for both. Maybe in the first track, it's going to fire in the beginning, and then the second, in the new environment, it's going to fire at the very end. So there's no correlation either. So it's totally different encoding.
Okay. From this an additional of 247 new place fields were present in the new environment that tiled the track. From this result, we can conclude that global remapping is occurring. A whole new set of cells are being formed for the representation of the new environment. The next question is, when are these place fields in the new environment being formed? If we know when these place fields are being formed, we can test whether synaptic plasticity is uniquely occurring during this period, and if so, what role does it play? In order to test when these places are formed, Schifrin and Dobek track calcium transients in the stomach throughout the whole traversal. So here you see on the x-axis the number of labs, and on the y-axis number of place fields. And you can see that more than a third of the place fields are being formed in the first lab, 35 cells are formed in the second lab, and in total 80% of the place cells appear within the first 8 labs. This tells us that the global remapping occurs very quickly. Now that we know that global remapping is occurring, and we can track exactly when it's occurring, now we can ask during that time what is occurring at the dendrite. The researchers define a measure called BSP, branch spike prevalence. So every neuron has dendrites. We count the number of the dendrites, and for every neuron we count the number of branch spikes, and the BSP will be the ratio between them. Okay. The reason this measure is useful is because synaptic plasticity is occurring at the level of the branch, so we are interested in studying branch activity specifically. What they see.
I just want to comment that you should understand how difficult it is to record in the dendrites while the animal is viewing a space that is moving. The animal is also running on a ball, and you have to record from specific location of a dendrite of a neuron which is filled with calcium dye. This was never done before. Very, very difficult project to do, especially I don't know what you painted there, but I guess you want to show there are many branches, and you want to record from different branches of a neuron during this plasticity learning of becoming a placer. It is very heroic, very dramatic, successful, really a breakthrough in terms of connection between dendritic activity and behavior. That's very relatively something. That's why the paper is presented here.
So there's that. The average BSP for individual cell goes elevated when the somatic place field first appears. You can see it here. And decrease with lab number. They did not occur when the mice were first exposed to the familiar environment, and the BSP throughout the new environment was significantly higher than the familiar environment. So this means that dendritic activity that would underlie synaptic plasticity is occurring during the formation of new place fields.
Is that clear? Is that clear what you see here?
This graph is in average, but it occurs for every cell.
But is it clear what we see here? What is this 0.8, or what does it mean that it goes to 0.2? Or what does it mean? Is it clear to all of you, or not?
Can't say.
So I mean, in that you're looking at the number of branch spikes. So here, let's say for the
average over for F, it's fairly low. There's no change when you're first exposed to the similar environment. You're not going to have more spikes in the branches, in the dendrites. Whereas here you have this, at first exposure you have this high level of branch spiking, and then slowly as the mouse is already encoded in the new environment, that spiking is going down. But right here in the very beginning, when the place fields are being formed, that's when you have all this dendritic activity. So it's telling you that these dendrites are performing an essential computation in encoding these place fields. That they're playing this role that they're going to be, during the time when the cell is learning these place fields, that's when you have this, dendritic activity at its highest. Is that clear?
Okay. I mentioned before that dendritic branch spiking and somatic firing can be dissociated in serum place field. And because of that, we want to ask whether the location of branch spiking on the tract during initial exposure in the new environment was an indicator where the new place field would be by the end of that section. Okay? So they measure the BXP of the dendrites during initial exposure for each location, and then they look to see where the mean track location of somatic place field were formed for that last area. This, they found that BXP was significantly higher while the mouse was in the location where the place field would be formed compared to other locations. It's cool. Okay. This results, the fact that more branch spiking is occurring during place field formation, and that this branch spiking can predict the location of where the place fields will correspond to, indicates that CN1 synaptic plasticity is occurring during the window in which place fields are forming during exposure to the new environment. And that one is over to now.
What does that mean? How is it outside of the...
It's like you can predict the location, meaning if you could just use the spiking of the dendrites during formation to predict the location of where the place field is going to be formed. While the mouse is in that location, that's when the dendrites are spiking. So you know that soma is going to become a place field for that location because that's when the dendrites. So it's telling you that it's essential for that encoding that specific location. Okay. So here you see that not all of the cells are being formed in the first lap, right? We saw that there's this rapid remapping, but they're not all occurring at once. You have a large number in the beginning, but there's still 2/3 of the cells are being formed in later laps. So the question is that there's no somatic firing occurring while the mouse is in that location. So you're not going to have, if you want to study synaptic plasticity, the basic principle of neurons, there's no somatic firing during that time.
That's very important. I don't know if you got it, but it's important to understand that there is a calcium signal in the dendrite during this, this period where you see a lot of activity, but no spike in the soma. So the cell is not yet a place cell, so to speak, in the classical sense, because there is no output from this cell yet. But the dendrite starts to be very active before there is somatic output. Already the dendrites are learning something. That's the main interesting message, that there is some stage of plasticity in the dendrite and the soma is still quiet, which is interesting. How come that the soma is quiet and the dendrites are active? But I guess you will tell about this later on. So that's a very unexpected result. There is a lot of activity, depolarization in the dendrite, a lot of calcium coming in, but the soma is quiet. So it's not yet a place cell. It is becoming a place cell. It is learning to become a place cell in terms of output. This is a strong result.
Okay. Yeah, so the question that the researchers are basically asking is synaptic plasticity occurring in the delayed onset place field, right? These cells that are becoming place cells later on, there's no somatic firing. So can we see a mechanism of synaptic plasticity? So what they want to do is, there's not going to be actual branch spikes to record. There's no branch spikes during this time, but they can study localized calcium transients. So there's still some depolarization. It's not enough for an actual branch spike. There's a little depolarization. They want to see, can we measure this depolarization, and what's that going to tell us about the formation of these place cells? So what you want to see some kind of activity there to determine whether there's synaptic potentiation. So they looked they found across 17 delayed onset fields, they found 33 calcium transients were detected. So they did find that there was some kind of calcium, activity going on, even though there was no somatic firing. So they detected 33 calcium transients. 24 out of 33 encompass a single branch. So what that means is that it's not just at a small spine, because that might not be enough for synaptic potentiation. You need enough activity at the branch of the dendrite in order to eventually drive synaptic potentiation. So they found that when there was calcium transients, it was extended across the whole branch, where eventually that would be enough for synaptic potentiation. And they found 30 out of 33 invaded an area, both encompassing both the shaft and the spine. So again, what they're showing is that when you see these calcium transients, they're not just very localized at different branches or a little bit at each different spine, because that might not be enough to drive synaptic potentiation. The kind of calcium transients that we're seeing is on a whole branch, which means that it could, in theory, drive synaptic potentiation. So that's the first thing they
Can you
showed.
explain what we see in the figure?
Yeah, so here you see, basically, this is going to be a little bit more relevant later on, but you see as the mouse is traversing the environment, so here it's the track location, so you're going to see basically the calcium transient level. So here, it's pretty steady, and then the mouse gets to a certain location, and you're going to get a spike in calcium transient. So this is going to be very important.
The red
Yeah, exactly.
The red is a dendritic spike in some dendritic location.
Right, so this is telling you that in this area there's a calcium increase in a very specific area. So this is going to be important because it's saying that this cell is going to eventually encode, eventually it's going to drive somatic firing in that location.
But
Right now there's no somatic firing.
There is a soma, if you look at the soma response,
Yeah.
there is also a calcium response in this part of the soma as well.
Right, but it's not large enough it's not large. It's not large enough to drive an action potential.
So you think there is no action potential, still there's calcium signal,
There's some calcium signal,
but not an action potential.
but there's no action potential. Through the potentiation of the dendrites, that's going to drive the somatic potential. Yeah. So this is just one result in favor of these localized dendritic, transients occurring. The next thing that they found is they saw that 22 out of 30 calcium transients occurred within the boundary of where the somatic place field would later form. So if you want to see, right now there's no somatic firing, but eventually there is going to be somatic firing. It is going to become a place field. So you look, okay, where exactly is it a place field? And then you see, where do these calcium transients occur? Can these calcium transients predict where the place field will later be? So you see that overwhelmingly it occurs within where the place field forms. And you also notice that it occurs actually at the beginning of these boundaries. So the researchers didn't explain why that's significant, but I mean, intuitively you would think that it's going to take some time for the synaptic potentiation to occur. So immediately, as soon as the cell is being exposed to a new environment, you have this increase in calcium transients. That it's going to give it the time in order to form an actual, place cell, so that the somatic firing is also occurring. So that's the second result that's important. The third result is they do a synaptic simulation. So what they do is basically they mimic synaptic input through a glutamate uncaging technique, and they target these dendritic spines.
In vitro.
This is all in vitro, yeah. And what they see is that these localized transients have amplitudes and durations similar to those recorded in these mice. So what that's telling you is that maybe one could say that these dendritic calcium transients they have nothing to do with synaptic input. Maybe there's some other mechanism that's affecting them. So what they're showing them is that the durations and the amplitudes of these dendritic transients look exactly the same as if they're what we knew for sure there was a synaptic input. So what that's telling you is that it does seem like it's a synaptic input that's driving these calcium transients. So basically, through these three arguments, that in the absence of somatic calcium transients, this is occurring. This isn't occurring with somatic firing. It invades an area larger than a single spine, right? It's on the whole dendrite, branch, meaning there's enough there for it to drive potentiation. They have amplitudes and durations similar to synaptic input, and it predicts where the place field is going to form. That tells you that this mechanism is very important for, this calcium transients are driving through synaptic potentiation, are going to eventually drive these place field formations. Is everyone good with that? Okay. So the next thing that they looked at is dendritic inhibition. So we know from one of the Idan's papers, and there's a lot of papers that have come out that show that dendritic inhibition plays an important role in synaptic plasticity. So I think you showed it by excitatory neurons, but it plays a role in all, in all sorts of mechanisms of plasticity. So in general, there are two kinds of inhibition. There are interneurons which target basal dendrites and COA1 pyramidal cells. This is targeting the dendrites. And the other one, you have basket cell axons that produce somatic inhibition. So these are two different groups of interneurons, right? One is targeting the dendrite, the other one is targeting the soma. And they want to see what role does this have to play in this whole mechanism of place field formation. So first, they target the interneurons which inhibit basal dendrites. They use a fluorophore basically to see how much, they basically image the axon to see how active it is. And what they see a really fascinating result, because what they see is that axonal activity in the interneuron which is going to inhibit these dendrites abruptly decreases during the switch from the familiar to the novel environment. And then that gradually returns to the F level. So you have this, as soon as from the familiar environment the mouse is exposed to the new environment, this dendritic inhibition rapidly decreases and then eventually it comes back. Right? You can't have sustained inhibition. Eventually it's going to come back to baseline levels. But while the mouse is first exposed to the new environment, there's this rapid decrease in inhibition. And you don't see the same result in F. It's not that the mouse just all of a sudden started to run, for example. That doesn't affect the level of inhibition, only when it's exposed to a new environment. So this will be very helpful for learning, because if there's less dendritic inhibition, then it means that the dendrites can do more. There's more activity. That activity can affect the soma. That's going to be very important for synaptic plasticity. Then they looked at somatic inhibition, and they measured the basket cell axon activity to measure inhibition. And here they saw the exact opposite effect. So they see that there's actually a decrease when they're moving from rest to running, which isn't necessarily useful for plasticity or learning, but abruptly increase when environments switch from F to N. So these interneurons, which are inhibiting the soma, are rapidly increasing as soon as the mouse is exposed to a new environment. So what that means is that there's not going to be an output. These neurons are basically inhibiting any output from these cells. So even though the dendrites have lower inhibition, so the dendrites can learn and can adjust their weight, the soma is inhibited. We don't want the soma firing and sending that signal to the next neuron while these neurons are still in the process of learning. So you have this amazing coordination between the inhibition to the dendrite and inhibition to the soma. Dendritic inhibition is rapidly decreased, and somatic inhibition is rapidly increased. But what that's also telling you is that it's a synaptic plasticity mechanism, right? In order for synaptic plasticity to occur, the dendrites need to be uninhibited, the soma needs to be inhibited, and that's exactly what you see here. So this is another indication that synaptic plasticity is playing a very important role in this place field formation. So, there's a quote: the reduction in inhibition could create a time window in which branch spikes induce synaptic potentiation that will drive somatic firing during place field once inhibition returns to F level. So now another experiment that they did is looking at NMDA. So NMDA, we know, plays an important role in synaptic potentiation. So what they did is they knocked out a gene encoding NR1 subunit. So I think many of you know that there's an NR2 subunit, there's an NR1 subunit that's essential for the NMDA receptor. And they wanted to see if we knock it out, if we block the mechanism of synaptic potentiation, what effect is that going to have on this place field formation? Right? Remove synaptic, potentiation. What's that going to affect? How is that going to affect, this whole mechanism? So what they found is that the fraction of place fields formed in N was significantly reduced compared to the wild type. So again, there's two groups. There's a wild type group, which they don't touch. These mice are healthy. There's no NR1 knockdown. And the group that has the NR1 knockdown. And you see the significant difference between how many place fields will form. And the place fields that did form, so it's not that it's zero. There still are some place fields that do form, place cells that do form, but there's a reduction in somatic firing frequency. So they're not as stable, they're not as robust in their firing patterns. This is, they targeted in these cells in CA1. Yeah. So I'll show you just another picture here. You see, this is a very great illustration. The wild type here, this is all the place fields, all the place cells, a good amount of them. Here, when you do NR1 knockdown, there's a significant amount of less place cells. So a lot of them are not formed. And even the ones that are formed are much less robust, are much less reliable. Sorry? Behavior, yeah. So they show also there's behavioral deficits. In this experiment, they're not looking at behavior. They're just looking at the number of play cells formed. But previously, they showed that behavior is also affected. Yeah. Yeah. So then, okay. So we see that NMDA has an essential role to play in the actual formation of play cells. But the next question they want to ask is, what about the cells that do form? Can we understand better the mechanism of how the NMDA plays a role in their stability of, the long term? So what we did is they measured detectable somatic transients in the first 8 laps versus the last 8 laps, right? So in the first 8 laps, these cells are still being formed, and in the last 8 laps, they should be formed, right? 80% were formed by the first 16 laps. So by the time you're getting to the last 8, there should be a robust and complete, formation of these play cells. So they wanted to compare how would it look different for the wild type group and for the knockout group. So for both wild type and knockout, the somatic transients first 8 significantly higher than the last 8. So that makes sense, right? You have, even in the knockout group, you still have some play cells being formed. So you're going to have a higher somatic level, a higher level of somatic, transient. But what they found also is a much greater reduction in transient number in last 8 for NR1 knockdown versus wild type population. So here, if you compare this group to this group, this is in the last 8 laps, the wild type group is a lot more stable than the NR1 group, right? The NR1 group is not responding as robustly to these places that they were supposed to be encoding. So that's sort of in terms of the experiments that they did. So now they sort of present this in their discussion, the theory of these two pathways. So the first pathway is that the sum of synaptic input is large enough upon initial exposure to drive action potential firing in a particular location. So that, right, those cells that are formed in the first lap, they're exposed to a new environment. It's very reactive. It's very responsive. These cells start firing. There's an action potential. It's encoding that new environment. And in a sense, that doesn't necessarily require synaptic plasticity in order to form as a play field. The second pathway is that the sum is initially too small, right? You don't have initially, there's no somatic firing. Initially, it's not a play cell. But after the synapses are potentiated, they become strong enough to drive somatic firing. So they have the potential to become play cells, but they require synaptic potentiation in order to become play cells. And, there's a support for this that knocking out NMDA reduces play fields formed by 50%. So you can't say that synaptic plasticity is required for the formation of all cells. It requires about 50%, is what they claim. And they have this beautiful diagram. They basically, I don't know if you can see it, but they basically present these two mechanisms. So synaptic plasticity is necessary regardless. But in the first mechanism, synaptic plasticity doesn't form these neurons. It doesn't form the play cells. But what it does is it stabilizes them. So if you want stability over time, then you need synaptic plasticity. So here you have somatic play fields firing, right? Initial exposure. Right away the soma is firing. These dendrite branch spikes are pretty high. And this is during a time of reduced dendritic inhibition. And then you have this potentiation, so that here, once the dendritic inhibition returns to baseline levels, then there's still a stability that occurs. So according to the first mechanism, synaptic plasticity isn't required to form these cells, but it's required to keep them stable when the dendritic inhibition comes to baseline levels. Whereas here, it's not just that they keep them stable, it's that they actually help form them. So here you have reduced dendritic inhibition. Originally, upon exposure, it's not enough to drive somatic firing, but you have these branches that show a calcium transient. And then you have over time, through synaptic potentiation, then the soma will also fire, right? And then eventually, when the dendrite inhibition level comes back to baseline, it doesn't matter anymore. This is stable enough where it's firing. Is everyone clear on the two mechanisms? Yeah? So again, synaptic plasticity is essential. The question is, it's not always essential for the formation. Sometimes it's also just essential for the stability of these cells in the long term. So we had a few comments here. This is something we actually when talking with Idan about. It's this amazing mechanism that you have the coordinated activity of somatic and dendritic inhibitions occurs by two distinct set of interneurons. How do they coordinate activity? So here you have exposure to N in the soma, rapid increase in inhibition, so that the soma is not firing. But here you have a rapid decrease in the dendrites, so the dendrites could learn. But yeah, it's not like these neurons and these neurons are the same neurons that are inhibiting this cell. It's a two distinct set of inhibitory neurons. So the question is, how do they coordinate their activity? That's something that I mentioned and we thought was really interesting.
Is there any evidence that they do that?
Sorry?
Is there any direct evidence by recording these inhibitory neurons?
That they're doing the inhibition? Yeah,
They're
that.
doing inhibition in the right way, the right timing.
Yeah, so this is occurring right exactly as the mice is exposed to the new environment. So this is the point when you want the learning to be occurring.
More inhibition, more firing rate, and the other one expects less, right?
Well, this is exactly what you'd want for learning. But what's amazing is that it's not like
But this is experimental results, so they recorded from these two populations of interneurons during behavior. So they recorded from the interneurons.
Interneurons?
These are from the interneurons.
This
So
is
the basket
interneuron
cells,
activity.
the basket cells that inhibit the cell body of the postsynaptic cells, the basket cells that inhibit the pyramidal cells start to fire very high, inhibiting the cell body, and at the same time they see that these other interneurons, that they mostly go to the dendrite, like Martinotti cells, which are inhibitor cells going to the dendrite, they decrease the activity and they enable the activity in the dendrite. So it's a coordinated inhibitory activity.
This is a fluorescent from an inhibitory cell.
Yes,
Exactly.
yes, this is the inhibitory cell.
But these are two distinct groups of cells, not that meaning how do they know how to coordinate? That's sort of the question.
Who coordinate these two? If one goes up, we don't understand the network coordination, but that's a fact, experimental fact.
Yeah, but this is essential for learning. You want both of these effects in order to drive learning. So that's the first comment. The second comment is, so they make this claim in the paper, they don't really explain how. Some place cells are formed without synaptic potentiation. Rather, they are pre-strengthened prior to novel environment exposure. So what they say is that, right, the one pathway that says that you don't need synaptic plasticity, what they say is that there's already some kind of ensemble that's ready. It's there ready for as soon as you see a new location, it's going to start firing and it's going to form the place cell. So, I mean, it's a very interesting theory, but they don't really explain it. They don't explain how you can have this prepared set of neurons ready to fire as soon as they're exposed to a new environment. So that's something that it would be nice to have sort of explore further and understand this mechanism further. We thought it was interesting, but how do you know how does it work? It's a little vague. It was left a little vague. And the third thing is, okay, assuming we sort of accept this, then we could ask this question, right? When we're recording, right? Let's say this neuron is going to become a place cell. There's a lot of other neurons that are not going to become place cells. So the question is, are these localized calcium transients, are they necessary and sufficient to drive eventual place field formation? Maybe there's calcium transients that's occurring in these other cells. It's just that, because they're not pre-selected, they're never going to become place cells. But this cell has both a calcium transient and it has some pre-selected mechanism, and therefore it's going to become a place cell. So again, the question is, these localized calcium transients, are they, we can accept that they're a necessary condition to drive eventual place field formation, but are they a sufficient condition? Are there other parameters that need to be in place in order for these localized calcium transients eventually to drive this place field formation? Everyone clear on the question? Okay, so that's basically it.
How would you attack this question?
So I would record, during this formation, I would just record the calcium transients from these other cells, the ones that don't become, because there's not that many cells that are becoming place cells with these calcium transients.
You want to say, let's say that I record from a cell that is not becoming a place cell.
Yeah.
Maybe the dendrites are still active with depolarization, calcium and all that.
Exactly.
And in this case, you will then say that it's not, that it's happening, but it's not necessary.
It's not a sufficient condition. It doesn't determine whether this will become a place cell. How do you know? Meaning, you never recorded it from these other cells, so you don't know whether calcium transients is a property that's present for all these cells. And there's something, they claim that there's some pre-strengthened parameter for these specific ones that do become place cells. So maybe that's what's determining the formation of these cells.
The other direction is to take a cell that you know that becomes a place cell, and you don't allow, after allowing it to become a place cell, you block, but that may be too late, because already the synapses become strong.
Yeah.
I was thinking maybe we can block the calcium transient
Is that good?
while it happens, so not allowing the synapses to become strong by blocking the calcium signal, but that's not so easy to do per cell.
Right.
So you have still first to see that the cell will become place cell, but if it already became place cell, the synapses are already strong.
Right. And I can accept that it's a necessary condition that would mean that if you showed that they still don't form, that would show that it's a necessary condition. I'm not bothered by saying that it's a necessary condition. I'm asking if it's a sufficient condition or if there's other conditions that are in place, because they just don't record from any of the other cells, so they can't compare cells that become plate cells versus cells that don't become
Can
plate
you
cells.
go very fast backward to this one when you saw the transient signal in the different dendrites? Back, more. Here.
Yeah.
You see that if you look at lab number 26 or lab number, what is it, 36 there,
Mm-hmm.
you see that after learning, so you learn in the very beginning, few labs, yes? You learn fast, and there is this calcium signal, the red signal in the dendrites, and then there is no red signal in the dendrites anymore after learning. That's something you didn't mention.
Well, that's the dendritic inhibition coming back,
Yeah,
right?
because
Meaning
you have to, that's an interesting point. After learning, the synapses became strong, but you don't need any more the calcium signal in the dendrites, so you block the calcium signal, but there is an output of the cell. You can see in the soma, there is a much stronger output. So there are spikes in the soma, but the dendrites do not have any more calcium signal, because the synapses are already strong. So you use the calcium signal to teach the synapses, then you block the calcium signal because you bring back the inhibition of the dendrites. So inhibition blocks the learning. The learning ended, but the synapses are already strong. So the place then in place. It's an interesting switch between the period where you plastically learn by calcium signal in the dendrite. So you see the red signal in the dendrite during learning, but no synaptic, no somatic output. And then in the middle column, you don't see anymore the calcium signal, but you see a spike output in the soma. Okay? So the learning ended because the synapses became strong. It's a very powerful paper.
Can you explain the change in the spike in the soma between lab 26 and 36? Because we don't see any calcium working there, but we do see that it's stronger.
right. So there's an increased somatic firing. It's not quite as strong as lab 36, and there's already less dendritic inhibition. So it's a good point. I mean, it seems like either this level of somatic activity is already enough, where it's already being formed, it's already stable, that even without these dendrites, neurons are fired together, wires together, the soma is already firing enough that over another 10 laps it's going to fire stronger, but this is already enough of a firing, whereas this is not.
Why stronger, do they say? Because you're right, there is a...
They don't explain that.
Seems to be a stronger activity.
But it's not because of the dendritic calcium.
No.
Well, anytime you have more practice, you're going to have more sensitivity, right? If you have 10 laps to practice, you're still going to be a little bit more. Now you don't even need the dendrites anymore. From the soma's firing, from the pre-synapse. Now you're going to have.
But something has to change in order for the soma to fire more.
But these are calcium transients. The dendrites still can have activity, just.
Yeah, but they don't explain the mechanism.
Yeah, they don't
just show
explain.
the result, but you don't know whether the synapses continue to become stronger somehow.
Yeah, it's a good
It's
point.
not in the paper.
They don't explain exactly the difference between 26 and 36. Here you see a clear difference between lap 8. The first 8, they focus on the first 8 laps. This is sort of the rest. But it's a good point that 26 and 36 is not. I think it's just because more practice.
How does the somatic inhibition
Yeah, why not
go?
the other reason?
How quickly?
No, the somatic inhibition, does it just go lower and lower from the beginning, or does it...
It's, so we can see here.
Just a graph of it, we can...
Yeah, so, I don't know how helpful this is, but, you see there's a pretty,
It doesn't go to 36,
You
so
could
maybe
feel
it's
it,
yeah.
yeah.
hanging.
Is what?
But it is releasing like slowly the inhibition, so that could
Right.
that explain the,
Well, they
Increase
have
in the
Bepstein
soma.
to
I mean,
22.
there is less and less somatic inhibition
Yes,
with time
exactly.
for some reason.
Uh-huh.
Because inhibition should also participate in plasticity with cells. But you're right, it goes down, and then the soma can fire more.
But
and
here
more.
it's still lap 22, so I don't know why from 26 to 36 it would make a difference. It's a good question. Yeah. Well, once it gets to baseline, there's like a baseline level here. You could see an F if there's the same baseline.
Okay. So this
That's
is the
it?
first demonstration of the correlation between changes in the dendrite and behavior. But it also says, of course, that each neuron, each pyramidal neuron, many of them receive input from all the environments. Yeah, so in principle, I could be a place cell here, or I could become a place cell there. Anywhere I could become a place cell, in principle. But something happens to me as a cell in this location, and some of my synapses from this location becomes active. And now, they fire the dendrites, calcium, and I become a place cell there. But I could become a place cell elsewhere. There is another paper in this same neuron, back-to-back paper, showing that you can enhance, you can force a neuron to become a place cell by a little bit injecting current through when the animal navigates, you can inject current to the dendrites, depolarize the dendrites yourself, and then the cell becomes a place cell for this location. You can force a cell to become a place cell anywhere you want. So the synapses are already there. You just have to decide which group of synapses are those who will make cell fire here and not there. And, potentially you become a place cell anywhere. Very interesting system. Okay. Thank you very much.
Thank you.
I hope you learned something in this.
Thank you, Nan.
Okay. אבל אם תרצי באיזושהי שלב, אם תעברי ולא תגידי משהו, תבוא אליי, תגידי, מיני הרצאה קטנה על המקומות שחסרים לך.
אתה יודע להגיד לי רק דרך הדפו דף? אולי הגעת עד הסוף,
לא,
כי זה מצגת כאילו מאוד מאוד גדולה.
לא הגעתי. גם זה אפילו אתה. בגלל שאת לא יודעת מתי הפסקתי, לא יודעת מתי זה יסתיים.
חשבתי אולי נעשה יחס לפי איך שעשית בשיעור הראשון.
לא, אני אשמח בדיוק את זה. באמת יש שם יותר ממה שאפשר לדבר עליו בשני שיעורים.
ששכחתי שהישיבה עכשיו מתקיימת.
זה ממש משהו שכחתי.
נכון. כן. כן, כן, כן. כן, אז פרוסיס, אז קצת דיברתי על, ההרצאה הייתה על החלק הזה של החישובים בדנדריטים, ראיתי דוגמאות של איך אפשר לעשות חישוב של כיווניות של תנועה של נקודת אור בעולם. אני לא יודע אם ראיתי את זה עדיין, או שלא אומר לך הרבה מה שאני אומר.
ראיתי עד הפעם הקודמת, שיעור לפני.
כן, אז דיברתי על איך אפשר לעשות חישוב של איך אתה זה מחשב עם נקודת אור זאת וכיוונות אור ודברים האחרים.
כאילו נגעת בחישוב ראייתי, כאילו...
בתור דוגמה, איך דנדריט עם סינפסות יכול לקחת נקודת אור מן העולם ולהוציא פלט שהוא קשור לכיוון התנועה. אז לא תביני אולי מזה.
כן, אני אקרא.
אם לא תביני אז נדבר על זה בפעם כ-FT. זה לא אבל ממילא, אבל זה מה זה קונקטורים. אמרתי ואיך אנחנו...
זאת לא עבד בווידאו?
לא, יש לנו וידאו של עוד לא. זה וידאו של EM שחותך אותי את יסוד ולשחזר אמיתי כזה. אז ממילא, אבל זאת התוצאה. אז שהוא הרב הרטינה, הוא האנטומי והמבני, שהתאים הפרסינפטיים, אמרתי, בטא הפרסינפטיים וזה, כשאתה מסתכל על מספר הסינפסות האינהיביטוריות על התא הזה, אתה רואה שמהצד הימני יש יותר סינפסות אדומות, השאלה שלי הייתה נקודה שזזה בכיוון הזה, היא הייתה קודם מפעילה את התא הפרסינפטי והצהוב, הוא היה עושה אינהיביציה על התא הירוק, התא הירוק לא יכול היה ליצור ספייק. אם הייתם מבין קצת את הנקודה מצד שמאל לצד ימין, זה פחות אינהיביציה,
כן, ואז
של
הוא
התא הזה, ואז התא
יורד.
מתקנת אותו.
כן.
וזה היה הבסיס האנטומי, במקרה הזה, ל-direction alternatives, כן, זאת אומרת, זה דיברתי
אז
קצת.
בתאים כאלה יש לך פשוט בצד מסוים
זה
יותר
אסימטריה.
אינהיביציה. כן, זה לא סימטרי.
זה לא סימטרי מבחינת אינהיביציה, זה המנגנון במקרה הזה. דיברתי גם על מנגנונים אפשריים ל-directional selective. אתה צריך משהו שהוא לא סימטרי. בין